Thank you so much, everyone. Welcome to lecture 4. Right, so review first what we were doing last week. Was studying alkene. We looked at a few examples of important alkene compounds from natural sources. The structure of alkene was explained. This is somewhat different than structure of alkane. So I want you to probably just give some attention to how it is different than alkane. Remember that alkane was tetrahedral, meaning in 3D form, while alkene is trigonal planar, so the double bond is on one plane, and then we only have two groups which could be inside or outside, but no, the carbon will always be on that plane. So that's why we can have cis-trans isomers in alkene, while for alkane we could have different types of stereoisomers, which we will probably discover in some of the later chapters. Besides that, we looked at the nomenclature rules. So all the basic rules which we studied for alkanes still apply in alkenes. What is the change here? That we have to give priority to carbon-carbon double bond because that's our functional group. So while numbering, we have to give numbering from the end where carbon-carbon double bond gets the least number. And all the other rules still apply. Cis-trans we looked at because alkene is kind of rigid. So the two groups which are present on each of the carbons of the carbon-carbon double bond could be placed in two different ways. Either the bulkier groups are placed on the same side of the carbon-carbon double bond, or the bulkier groups can be placed on the opposite side of the carbon-carbon double bond, which make them into different stereoisomers. When they are on same side, we call them cis isomers, and when they are on opposite side, we call them trans isomers, right? But cis and trans is a bit less systematic. We can see many cases of this nomenclature being failed to name the structure, which you will see in your tutorial section soon this week. So that's why the more systematic way to name these stereoisomers of alkene is E and Z nomenclature. So for that, we looked at how this systematically tells one isomer apart from the other isomer. So in this case, we go with different priorities based on the atomic number, just like that. See, bromine is higher atomic number, so it gets one priority. While in this case, methyl has carbon, so carbon has 6 atomic number as opposed to hydrogen's 1. So this gets high priority. Now high priority groups are on the opposite side. So this makes the molecule E, and if they were on the same side, that would make the molecule Z. This topic is really important for your exam as well, and we will do loads of practice for this in this week's tutorial. So please try to make it in time. Right, then we looked at few examples of the commercially important alkenes such as ethylene or propylene, and that's where I think where we talked about the stability of alkenes in case when we have different substitution on the carbon-carbon double bond. Generally speaking, the more substitution is present on carbon-carbon double bond, more strength the carbon-carbon double bond will get from the electron flow of those electronic groups which are present on the carbon-carbon double bond. In case of cis and trans, we could see that trans would be more stable as compared to cis because of the steric hindrance of electronic cloud in the case of cis alkenes, right? So this is where we left. I can take a moment for your questions if you have from previous class, or else we will start from this slide. I remember this is where we start. So any questions from the previous class? Anyone? All good? Right? The review is helpful, isn't it? But I want you to review yourself these things as well. Don't just rely on me. Sometimes I may skip it if I feel that, well, I have to speed up things a little bit. All good, right? Awesome. Today is one of those days actually. I do want to speed things up a little bit. We are half a lecture behind. Right, so now we start the chemical properties of alkene, and when we say chemical properties, this means that how they are synthesized or what type of reactions do they perform, right? So the first way they can be synthesized is called dehydrohalogenation. I think we have done this as well, right? Correct? So dehydrohalogenation means removal of hydrogen and halogen from the neighboring carbons. With the removal of two atoms from the neighboring carbons, we will have carbon-carbon double bond formed. But where this carbon-carbon double bond is formed is dictated by Saytzeff rule, which we will see from examples in next few slides. Yes, we had discussed this. E2 mechanism and E1 mechanism are two mechanisms by which elimination reaction occur. So dehydrohalogenation is an example of elimination reaction that generally occurs with E2 mechanism. So E2 mechanism, the departure of proton and halogen occurs simultaneously. That's why we don't have a proper intermediate of this reaction. We have a transition state where we show that how bond breaking and bond making is done at the same time, right? For this we need strong base which could, trigger the reaction and the removal of halogen atom from there. Beside this, of course, when we talk about any reaction, it's not only dependent on the reagents that we use. That's what we are talking about in this point, right? But more importantly, the reactant itself is also very, very, very important. So the type of alkyl halide that we have also is very important for the mechanism by which the elimination reaction will occur. So for any reaction to occur by E2 mechanism, the preferred alkyl halide would be tertiary and hindered secondary alkyl halides. What do you mean by tertiary and secondary alkyl halides? Well, alkyl halides, for starters, are alkane compound which carry one halogen atom in them at least. So alkyl halide, as the name suggests. Now, where the halogen atom is attached to the carbon, the next carbon is called primary carbon. So if primary carbon has only one further carbon, those compounds are called primary functional groups. So when we're talking about alkyl halides, primary alkyl halides would mean that the atom where halogen is attached, next to it is only one other carbon. When we have two other carbons attached to the carbon where halogen atom is attached, that will be secondary alkyl halide. And when we have three other carbons attached to the carbon where halogen atom is attached, that would be tertiary alkyl halide. And this stands true for every functional group. It's not about only alkyl halide. If we say primary alcohol, secondary alcohol, tertiary alcohol, still the same rule. So the carbon where functional group is attached, we always look at it. That next carbon, how many carbon that carbon is attached to further. If it's only one, then primary. If two, secondary, and if three, tertiary. That makes sense? So for E2 mechanism to occur, the preferred alkyl halides are tertiary and hindered secondary alkyl halides. While strong base would mean generally sodium hydroxide, potassium hydroxide, or small bases such as methoxides. If you don't know their names, don't worry about them. But of course you know hydroxides, right? Sodium hydroxide and potassium hydroxide. Those are very good examples of strong small bases. Right. reaction by which we can get alkene is called dehydration. When we say dehydration, it means removal of water. So you can remove water from any starting material if you use acid as your reagent. You have to use strong inorganic acids such as sulfuric acid, nitric acid, hydrochloric acid. They can remove water from the molecule. So this is what happens in this reaction. So we use concentrated sulfuric acid, and you see as a result the hydrogen and hydroxyl group which are present on the neighboring carbons are removed, and we get the formation of carbon-carbon double bond. This is just like the previous reaction. There we were removing hydrogen and halogen. Here we are removing hydrogen and hydroxide. No other difference except for the mechanism, which we'll see later. So these two were the reactions where we can get alkenes by elimination reaction. And just to remind you that what elimination reaction was, when something is being eliminated from your starting material. What was the other type of mechanism or reaction that we looked at earlier? Was the reverse of it, the addition reaction, in which something is actually added in your starting material. So indeed, we can also use addition reaction to get alkenes. To do that, we need to start with alkynes. So alkynes have carbon-carbon triple bond. If we, by very controlled reaction, only add one molecule of hydrogen to the carbon-carbon triple bond, then triple bond could be converted into carbon-carbon double bond. Hence, we can get alkenes from alkynes. Does this make sense? So this is just the reverse of elimination reaction, right? Because now we are not making new unsaturated bonds. We are saturating bonds with hydrogen. Or we can saturate them with anything. So that's why the name addition reaction. When I say saturation, that means lack of multiple bonds. Right? So here we have triple bond, which is one more than a double bond. So we can add one molecule to alkynes to convert them into carbon-carbon double bond. Now I want you to put some attention to this reaction because I use the word that if we use this reaction with good control, then we can get alkene. And to do that, we need some specific catalyst. Otherwise, what's stopping this alkene now to again react with hydrogen and be converted into all the way into an alkane? So do you see the flow of reaction here, right? We have triple bond, one hydrogen is added, converted into double bond. So why it stopped here? The hydrogen is still there, so it can react with hydrogen and the double bond can get converted into single bond as well. If you want to specifically get alkenes from alkynes, we need to use specific catalyst, which in this case is called Lindlar's catalyst. So when we use Lindlar catalyst, which is consisting of hydrogen in the presence of palladium and calcium carbonate, and then a specific organic base is used whose name is quinoline. So this combination was developed by a person named Lindlar, hence the reactant is called Lindlar catalyst. So the job of Lindlar catalyst is to stop the reaction at this point and don't do any further hydrogenation from here. Okay? So if in exam you get this kind of question, you have to use a proper catalyst if you want to stop the reaction right here. If you simply write hydrogen and not write these further details, then you may not get full points because hydrogen itself is very unspecific. It will be keep adding into the molecule unless all unsaturated bonds are converted into saturated bonds, meaning that all double and triple bonds are converted into single bonds. Right? So this is the first important thing for today, Lindlar catalyst. Please keep this in mind. Right. So as we saw the dehydration reaction of alcohols to be converted into alkenes, just like dehydrohalogenation the reaction occurs with E2 mechanism. So the dehydration of alcohols actually occurs with E1 mechanism. And how this is different than E2 mechanism is that here we do get a proper intermediate in the reaction. And then this reaction occurs in multiple steps. Now E stands for elimination, and 1 simply stands for that the important step of this reaction only requires one reagent. Remember that previously when we were talking about E2, I told you that base and the reactant, the alkyl halide, both of them are important in the important step because E2 only occurs in one step, so that step is really important. And in that important step, both of the things are really important. That's why we write E2 to differentiate it from the other type of mechanism, which is E1. So E is simple for elimination, but 1 suggests that you only need one reactant to control the rate of this reaction. Therefore, E1 mechanism. So what are those steps? Step 1 is protonation of hydroxyl group. Since we have the alcohol as the starting material of this reaction, and we are using sulfuric acid in this case to get the proton away from the alcohol, so the oxygen of hydroxyl group can be protonated because that's the only job of sulfuric acid, to provide the proton as being acid. So this provides this proton to the oxygen. Now have a look on the direction of the curly arrow. So direction of curly arrow in any sort of mechanism will always start from where the electrons are already present, because this curly arrow actually shows the flows of electrons. So electrons could only flow from where they are present and not from where they need to be. So here we have 2 extra electrons, right? So that's why we need to move or show the arrow starting the tail from here and then head from where they are going. So they get the hydrogen from sulfuric acid, and now it has an additional bond. That means, as well, you can think of this in a way that this has donated the this has donated the electron pair to the hydrogen. Now the electron pair is gone, so it will carry a positive charge, isn't it? Because it has given away the pair of electron to the hydrogen to make this extra bond. Now since this oxygen has a positive charge, meaning it is electron deficient, so in the second step, this bond can be broken. Meaning a bond is basically what? A pair of electrons, isn't it? So this pair of electron could go to oxygen. That's why we have made this arrow starting from the bond and towards oxygen, because that's where electrons are going. And why they are going towards oxygen? Because oxygen has a positive charge, which means that it needs electrons. So these curly arrows are important in making the mechanism or explaining how the reaction goes about. So you have to be a little bit familiar and sensitive about how you draw those arrows. They are pretty much different than this arrow or that arrow. So you know this arrow, this is for reversible reaction, but this is a straight line arrow. And these are curly arrows. So curly arrows only for the movement of electrons when you are drawing the mechanism. Anyway, this water molecule is removed just like that because oxygen is positive, so it can take away electrons from here. Now electrons are gone actually from carbon, right? So carbon will get a positive charge in this case. Just like previously, when electrons went from oxygen, it got a positive charge. So same like this here. Now electrons are going from carbon, so carbon will get a positive charge. This step is the rate limiting step and the important step for this reaction. And as you see here, that it only requires one starting material, hence E1 mechanism. So 1 actually represents this. That for the important step of the mechanism, you only require one reactant. Now you see how this is different from the E2 mechanism which we studied earlier. Alright, so this carbon containing positive charge ion is called carbocation. right? The spelling may look like carbocation or vacation or anything, but how it is read is carbocation. This is the important step in this reaction, yeah? Finally, what happens is that it has a hydrogen on the next carbon. So this can be abstracted, meaning that any conjugate base can abstract this proton, and when they take away this hydrogen, hydrogen gives away its pair of electron towards this carbon, because that's where the positive charge is. So electron flow will always be in the direction of where the electrons are needed. And of course electrons are needed where the positive charge is. That's why it suggests, right, lack of electrons. And as a result, we get the formation of carbon-carbon double bond. Any questions? So this is really important for you to understand that how a small difference in reactants and reagents can trigger different type of mechanism in a reaction. Although both of them are really similar looking reactions, aren't they? In both cases we are removing two atoms from the neighboring carbons, and as a result carbon-carbon double bond is getting formed. And what do I mean by both reactions? Meaning dehydrohalogenation as well as this dehydration. But because of the change in their conditions and starting materials, we can have different type of mechanism even within the same class of reaction. Both of the reaction are still elimination reaction, aren't they? But their mechanisms are totally different from each other, and different conditions will favor different mechanism based on what you actually need. Alright? Right, now let's talk about the Sage-Ziff rule. What did the Sage-Ziff rule say? That when you are making carbon-carbon double bond, try to make a substituted carbon-carbon double bond. In simple words, that's what Sage-Ziff say. If you have the option to make unsubstituted carbon-carbon double bond and a substituted carbon-carbon double bond, then the Sage-Ziff rule says always goes for more substituted carbon-carbon double bond. Here are the few examples. So you see that in the first example, where this alkyl halide is being reacted to potassium hydroxide in the presence of alcohol. Doesn't matter. Important is that alkyl halide is reacting with base, which is potassium hydroxide here. So what could happen here? Dehydrohalogenation, right? Because this is an alkyl halide and we are using a base, so dehydrohalogenation, isn't it? Now this reaction will occur how? E2 or E1? E2, unfortunately, yes, very good guess in the second attempt. Because when we use strong bases and alkyl halide, E2 mechanism is preferred. How do we know this? Experimentally proven. How did the experiment find it? When they performed this reaction and put it in a machine, they didn't find the formation of carbocation. So carbocation, since it's an intermediate, it can be studied, it can be isolated, but transition state is something hypothetical. So they didn't find carbocation in that machine, hence it's confirmed that this reaction only occurs by E2 mechanism. The options are that this halogen will be gone, that's no option. But we have two options here. Either a hydrogen from this carbon is removed or a hydrogen from that carbon is removed. How do we decide? Sage-Ziff rule. So if we remove it from here, then a carbon-carbon double bond will be formed here, which will not be substituted from the corner. But if we remove it from there, then the carbon-carbon double bond will be formed here, which will be substituted by methyl from both sides. So you see the difference now? And why this happens, I will explain you in next few slides. So when you get questions like this in exam, you have to consider Sage-Ziff rule. Although it's not wrong, if you make the carbon-carbon double bond at the corner, that's totally not wrong. But that will not be your major product. And when we ask you that what will be the product, we would generally mean major product. Or the question could say that only give the major product. right? Now that if you're practicing or you're learning it, try to learn the major product by itself so that you don't get the confusion later. And you get the reason why? Because substituted alkenes are somewhat more stable. That's why we can not remove the hydrogen from here, and we'll have to remove it from there. If you remove it from there, then the carbon-carbon double bond will be formed in between. That means we are getting a more substituted alkene as per the same before. Any question here? Are you able to see the other possibility? That we could remove the hydrogen from this carbon as well, right? And if we remove it from there, then carbon-carbon double bond will be here. But if we make carbon-carbon double bond here, that means that this carbon of the carbon-carbon double bond does not have any substitution, meaning that it will be less stable. Therefore, removing hydrogen from this carbon makes more sense. Alright? In this case, no problem because it's a symmetrical molecule. You can remove bromine from here, or hydrogen from there, or hydrogen from here. Does not make any difference. Because we will get a symmetrical molecule in the product. Right? Okay, what do you think? For this, where the double bond will come? Yeah, I'm asking to all of you, so anyone can speak. If this is the reaction, this is kind of fill in the blanks, which you can expect in your exam as well. Like you used to get in school, right? That a statement and fill in the blanks. So in chemistry, these are the fill in the blanks that you can expect in your exam. So if this is the reactant and these are the reagents, what will be your product? So now we are only studying about alkene. So the only possibility is that we will get alkene. But the question is, where will we get the double bond? Here? Here. Just like that, right? If you make it there, you will not get full points. You may get some points because that might be the minor product of the reaction. But due to stability, getting the more stable, meaning substituted alkene, prevails. Right? Right, in this case what happens? Where the carbon-carbon double bond will come? Here we have at least three possibilities. Either we can remove hydrogen from here, or we can use hydrogen from there, or we can use hydrogen from there. Right? If we use hydrogen from there, the double bond will come here. If we remove from here, the double bond will come here. If we remove from here, the double bond will come there. So where the double bond should come? Anyone from here maybe? What do you suggest? Which hydrogen should I remove? This or this? This? No? This? Or this? This one? This one. Alright, so someone said this one. They wouldn't be wrong. But this and this are actually same. Right? That was a trick question. So the only real question is either this or this. So if you remove it from here, the double bond comes here, which will not be so substituted. So of course there, right? Alright. Now let's talk about the reactions of alkane. We learned three reactions by which we can synthesize alkene. Dehydrohalogenation, dehydration, and hydrogenation using Lindlar catalyst. Right? I want you to probably make a note of this. if you'll have a habit of making a note of these reactions in a list, later you will not be struggling about, well, what happens when this reacts with that. So for every class of compound, you will see that we will have 3, 4, 2 numbers of different reactions. So it's a good idea to always make a list of them. Right, when we talk about the reactions of alkenes, so the first reaction is addition of hydrogen halide, where the halogen atom could be chlorine, bromine, or iodine. Of course, we can't have fluorine because that's like super reactive, and acetylene also is not that reactive anymore. So when we say halogen, it generally means chlorine, bromine, or iodine. Anyway, in addition reaction, as the name suggests, what will happen that the carbon-carbon double bond will be converted into carbon-carbon single bond. And then hydrogen will be added to the one carbon and halogen will be added to the other carbon. That's all. So you see hydrogen is added here, halogen is added here, and double bond is converted into single bond. This is an example of addition reaction. Right? So when we do an addition reaction, again we will have the similar dilemma as we had for Sedgwick rule. Based on the structure of your alkene. Now in this case, your alkene looks like symmetrical because this carbon has 2 methyl groups, this carbon also has 2 methyl groups. So no problem. You can add hydrogen here and halogen there. Or you can add halogen there and hydrogen here. It doesn't make any difference. But in case when we have an unsymmetrical carbon-carbon double bond, meaning that we have different groups on this carbon and different groups on that carbon. In those cases, where do we add hydrogen and where do we add halogen? That's same question as of Sedgwick rule, right? So for that we have Markovnikov rule. Markovnikov rule is actually the reverse of Sedgwick rule, which tells us, which helps us where we can put hydrogen and where we can put halogen. So in addition of hydrogen halide to an alkene, the hydrogen will attach to the carbon with fewer alkyl substituents. And the X, meaning halogen, attaches to the carbon with more alkyl substituents. Is this language useful? Do you understand this language? Substituents and blah blah blah. There's other way also by which I can tell you that you have to put hydrogens where there are already more hydrogens. That's what you need to do. And then of course halogen will go to the other carbon. When we will look at examples, you will know more. But beside that, that's about where the halogen will go. Technically speaking, that's what Markovnikov rule is telling us, right? Like where do we need to put halogen in case of when we don't have a symmetrical alkene. But how this reaction occurs, let's look at its mechanism briefly. So carbon-carbon double bond is having extra pi electrons, right? That's why they have 2 bonds. So meaning that they are kind of a nucleophile. They have, not to say excess electrons, but yeah, free bound electrons. Because they don't have a lone pair, so that's why I am a bit careful about my wording. So not to say excess electrons, but slightly loosely bound electrons. Carbon-carbon double bond is weaker in terms of its nucleophilicity. They are somewhat, you understand the term nucleophile, right? So nucleophile is a thing which has excess of electronic charge, right? When I say charge, it does not mean charge as of ion, but charge as of the density of electrons. So carbon-carbon double bond has excessive electron density. These electrons can be donated to something else, which is happening in this addition reaction. So they donate these electrons to hydrogen to basically absorb the hydrogen from hydrogen halide. As a result, we get the carbocation. Similarly, as we got for the elimination reaction, and then the bromide, which got separated from here, see that the head of this curly arrow is towards bromine because bromine is more electronegative. So it can take away the electron from this bond, isn't it? So when it takes away the electron, it will carry an extra electron pair, and that we can denote by a negative charge. So this negative charge can further attack on the carbon positive which was generated as a result of this addition of hydrogen, and we get hydrogen and bromine added to the neighboring carbons or the previously solved carbon-carbon double bond. Right? So here again we see the formation of carbocation. You will see the presence of carbocation in many different mechanisms. So I want you to probably, I don't know, understand this a little bit more. If there are any questions or concerns about the formation or utilization of carbocation in both the mechanisms which we discussed today, by all means you can ask them. Right? So do you see how hydrogen and halogen have been added on the carbon-carbon double bond? Now it's not carbon-carbon double bond anymore. Right? Okay, so this slide will be very helpful in understanding Markovnikov's rule because why this happens that you have to put hydrogen at a certain point and halogen at a certain point. So this has everything to do with the formation of carbocation. Right? So imagine that if this is your alkene, so now this is an unsymmetrical alkene. Why? Because one carbon has two methyl group and the other carbon has this group. Right? One hydrogen and other methyl group. So both of them have different groups, meaning that this is an unsymmetrical carbon-carbon double bond, right? Now if you put hydrogen here, it gives us a different carbocation. If you put hydrogen there, then it gives us a different carbocation. Right? In case of this carbon, the positive charge comes on the other carbon. In case of this carbon, the positive charge comes on the other carbon. Are you able to see this difference? That how putting hydrogen on different carbons can form the positive charge on the other carbon. Now this other carbon is what we used to call primary carbon, which is next to a functional group in this case. Anyway, let's not go into that detail. But you see that this carbocation has three other carbons, right? While this carbocation has only two other carbons, right? So which one you think would be more stable? The one with three, because the alkyl chain can also induce some electron cloud towards this positive charge, which is for the carbocation. That we call as inductive effect. But name is not important. It's only important to know that why this is more stable than the other one. But if you are, familiar with it, or you just want to memorize, so that's called inductive effect. All the other carbons will help the carbon with the positive charge by sharing some load of their electrons. So more the merrier. That's the general rule here. So if the carbon bearing the positive charge is attached further with many carbons, as many as 3, because it can only have 3 more carbons, one electron pair is gone, right? That's why it has a positive charge now. So if it has 3 further carbons, then it's called tertiary carbocation. And if it has 2 further carbons, it will be called secondary carbocation. If it only has one other carbon, then it would be obviously called primary carbocation. So the preference of their stability is as simple as that. Primary, then secondary, and tertiary is of course the most stable one. And the reason is the inductive effect of other carbons. They can propel the sharing of electron towards the brotherly other carbon, which now has a positive charge. Right? Although carbon does not have it has a moderate electronegativity, so it cannot pull electrons nicely, or it cannot also push electrons nicely. But this is the brotherhood among carbons, that when they have a positive charge, other carbons would somewhat, stabilize them with themselves. If they have any other atoms like oxygen or nitrogen, of course, they will be happy to give away their electrons. Right? If it was halogen, of course, it will be happy to take away further any electron if possible. But then carbon, which is not known to be electronegative or too much electropositive, would affect the stability of carbocation in these cases. So the general trend is tertiary is more stable. And when we follow Marconi-Kolb rule, we actually get the tertiary carbocation. That is the reason that we have to consider where to put hydrogen. Remember? That it makes all the difference in the formation of carbocation. If we put it at the wrong place, then we don't get a very stable carbocation. And hence we have to follow this rule, which tells to put hydrogen on the carbon which already has higher number of carbons. That's how you can see it. Right, so this carbon does not have any hydrogen, while this carbon has one hydrogen. So you can make up your mind easily. Just add hydrogen here. Then you will get the right carbocation, and then you will get the right product. That makes sense? Any questions so far? You want a break? You always want a break. You've never said me no for a break, which is okay, understandable. All right, we'll take 5 minutes. Thank you. Basically what I'm saying is tertiary almost always would be Alright, so we are starting at 5. We settle. Alright, class. So let's look at probably more examples about the application of pharmaceutical fuels. Right, so we have here again an unsymmetrical carbon-carbon double bond. No we. This double bond has different groups on each carbon. This one has these two groups, this one has these two groups. So when we add hydrogen bromide to this alkene, again we have two options. We can either put hydrogen there or we can put hydrogen here. Right? This is just the replicate of this. And I'm only trying to show you the different possibilities. But when we put hydrogen here, the positive charge comes there. And when we put hydrogen here, the positive charge comes there. So which of these carbocation is more stable? This one would be a bit more stable because this is tertiary carbocation, since this is connected to 3 other carbons. 1, 2, 3. While this carbocation will be less stable because this is a secondary carbocation, as it is only further attached to 2 carbons. 1, 2. Right, and that's the reason that your major product would be this and not from that. If you put the bromine there, that could still be your product, but only in minor quantity or percentage. So when asked in exam, always give the major product. If you give minor product, then you have to say that this is the minor product. And I don't remember the major product. Right? So you might get some points for that. Alright, the other reactions of water, of alkenes is with water, for example. So just like hydrogen halide, which we added just now, we can also add water molecule to alkenes. The reaction is pretty similar. You will add hydrogen at 1 carbon and hydroxyl at other carbon, and you you will still have to apply the Markovnikov rule because the mechanism is kind of same, which we will look in the next slide. The next reaction is addition of halogen or halogenation. So, no problem. Halogen, carbon-carbon double bond. One halogen, two halogen, carbon-carbon double bond gone. And then we will have, the alkyl halide with two halogens. Right? So if you use these reactions a little bit smartly, which I think you will later, not right now, because right now you're learning and this is the first class where we are looking at so many reactions. What I want you to build is the idea that, one thing with what reaction could be converted into the other thing. Later we will study about alkyl halides or alcohols or all the things which we are using today to make alkenes. Or we are looking at different reactions where alkene is getting converted into something else. So in this case, alcohol, isn't it? In this case, alkyl halide. So these are the reactions which we will again see in those chapters. Or when we were studying about the chemical properties of those functional groups, you will see few repetitions of these examples of reactions. So be a little bit more vigilant and it will all make a lot of useful things in your future chapters as well as in your exam. Do not be only specified about, alkene does this, alkene does that, alkene does this, alkene does that, or for any other functional group. So just look at the reactant and product. What is happening? What is being formed? What is being utilized? So you can always recycle some of these reactions in other chapters as well. Right, so the mechanism of hydration reaction, which was the addition of water molecule on alkene, goes like this. It has 3 steps. This is just an addition reaction, so it is not related to E1 and E2, but you will see that this is somewhat the reverse of what we did there. What happens is that as we established earlier that these alkene pi electrons are loosely bound, so they sometimes act like nucleophile, they can attack on other things and especially on hydrogens, which is freely available in acidic medium. So this hydrogen gets abstracted by one of the carbon and the other carbon gets the carbocation. Now the conjugate base of this acid, which was water, can attack the carbocation and we get the water molecule or hydroxonium ion attached to the carbocation carbon now, where a further deprotonation, meaning removal of hydrogen, can occur by again the conjugate base, and as a result we can get the attachment of hydroxyl group on the other carbon, where the hydrogen had already been added on the first carbon, isn't it? So you see that from the reactant to product, the green color hydrogen and hydroxyl groups have been added on the neighboring carbons. And the curly arrows simply shows the flows of electron, which you might have in your exam as well. So do some practice about drawing mechanism. So far we have done 3 mechanisms. So this is 4th mechanism. Free radical, addition reactions, the first one, and then 2 of the elimination reactions. Right? The 5th mechanism, which is also very important to see how this occurs, is, now this is about the halogenation reactions of alkene. So halogen can be added on alkene as well, as we saw earlier, but this occurs with a different type of mechanism. This does not happen like it should be, the one we saw earlier, hydration. This could also happen in the same way, right? But when experiments were performed, those intermediates were not formed here in this mechanism. So instead, when halogen reacts with alkenes, a halonium ion was formed. This unusual 3-membered ring having halogen atom as a positive charge ion is called halonium ion. So the bridge 3-membered ring is formed in addition. Now why this is important and I am boring you with this is because it impacts the stereochemistry of the product. Now imagine that these two carbons now have a bridge positive charge on their head, just like a house, right? So if this is the roof and this is the base, the next halogen would not be able to attack from the roof because of the positive charge. If it attacks from there, then the halide ion will take away the halogen atom and the reaction will go in reverse order. Right? So instead of top side attack, it can only attack from the back side, from the base of the house. And as a result, the two halogen atoms which are added on the alkane always need to be put on the opposite side. So with just this small detail, we can see that how the stereochemical destiny of the reaction is different. If you put the two halogen atom on the same side, you might not get full points in exam, and that would be chemically wrong based on the experimental factor that this reaction occurs with this mechanism. Do you see the gravity of this situation? I know that this may be an additional part of your memory for you to get it right, but the explanation is there. If you can see and understand and appreciate the explanation, then it wouldn't be a memory anymore. What you need to know that a halonium ion is formed. When halonium ion is formed, we cannot put two halogens on the same side. We have to put them on the opposite side. This becomes super important in synthetic chemistry, that how we can place the atoms on the groups where they are being attached in a given reaction. If we need them on the same side, we could still do it. Since my training is organic synthetic chemistry, so there are other reactions by which we could do that. But if we do this reaction, we will never get our desired alkyl halide where both halogens are on the same side. So this is why you need to know that which reactions and which conditions to utilize to get the product that you want in the lab. For the sake of your exam and your knowledge at this moment, all you need to know, because this is the only reaction we are studying about the halogenation of alkene, so this happens in anti-fashion. So this is called anti-addition. Why anti? Because these two groups are on the opposite side. So please note it down somewhere that the halogenation of alkene occurs in anti-stereochemistry. Now this is up and this is down. This means that one of them is out of the plane and the other one is inside the plane. That makes sense? And why this is happening? Because of the formation of halonium ion. Because one side is blocked, so it can only attack from the other side. And when we say other side, it simply means that if one was inside the plane, then the other one would be outside the plane. Okay? Any questions here? This is also kind of important. So if you get a question like this, and if you draw halogens on the both sides, you might not get full points, unfortunately. You may think that what's the big deal here? I mean, we did draw on the exact carbons where they were supposed to be, but then it tells that you don't understand the reaction clearly. Right? So that's why you have to put it on the opposite side. Right. Some more examples of the reactions of alkenes. So as you can see that alkenes have so many reactions, which means they will also be important for your exam, which means that it is very reactive as opposed to alkane, which only had two reactions, substitution and combustion. Here we have like so many different examples. And why these examples are important? Because from every reaction we are getting essentially something different. imagine that if you are working in a chemistry lab and you are making something, so you would need to make alkanes sometimes, alcohol sometimes, or alkaloids sometimes. So alkenes are pretty important about their reactivity. So here, another example that alkene can be converted into alkane, and this is the reaction that we saw in previous chapter as well when we were studying about the synthesis of alkane, wasn't it? That you can simply add hydrogen molecule on carbon-carbon double bond, which will be converted into carbon-carbon single bond, and you can see those two added hydrogens here. Right? One more reaction is oxidation of alkenes, which can be done by using potassium permanganate, which is KMnO4, a very strong oxidizing agent. So this reaction can be done on alkene in different conditions. First condition is in the presence of a base. So when we oxidize alkenes using the KMnO4 in the presence of base, the outcome of reaction would be different. And when we will use this reaction in the presence of acid, the outcome would be different. So first, look at the example where we are using basic medium. So we will get hydroxylation, meaning two hydroxyl groups will come instead of the carbon-carbon double bond. Now, there is no more carbon-carbon double oxide, carbon-carbon double bond, and we have added hydroxyl groups on each of the carbon. Right? If we use acid for this reaction, then what happens is that the carbon-carbon double bond is cleaved from the middle, from there, and you can simply put oxygen on both carbons. But what does it mean that we have converted alkenes into a totally different functional group? Carbonyls, ketone, or carboxylic acid, depending on what type of alkene we are taking. If your alkene is tetrasubstituted, meaning there is no hydrogen on any of the carbon-carbon double bond carbons, then we will get two ketones. But if there is at least one hydrogen, then we will get one ketone from the other side, and from this side we will get carboxylic acid. Because for it to be ketone, this carbon needs to be bonded with two other carbons. Right now it is only bonded to one carbon, so it cannot be a ketone. It might be an aldehyde, you would think, why not an aldehyde? But since KMnO4 is already there, so aldehydes are very easily oxidized into carboxylic acid. This is a reaction that you actually perform, not exactly this, but yeah, you have seen that how aldehydes are easily oxidized into something else. When you were doing Holland's test last week in the lab. So remember that only aldehyde gave you the silver mirror and not ketone. Right? So the reason is that aldehyde are very easily oxidized into carboxylic acid. And I didn't tell you that time that what that thing is. Remember that I kept saying that aldehyde get oxidized into something else, and silver is deposited on the walls of test tube, which appears as a mirror. So that something is a carboxylic acid. Anyway, this is a unwanted detail at this point because we will have a separate chapter for carboxylic acid anyway. So what happens that if your alkene is tetrasubstituted, you'll get ketones, and if it's trisubstituted, then you'll get a ketone and carboxylic acid. Okay? Alright? I cannot give you another break. We just finished our break. You're very uninterested at the moment, it seems.
Sure, come on, 5 minutes.
You will be like, not be able to catch up. Probably let me finish this chapter, then I will be done. Thank you. There are not many slides left, like 4 or 5 more slides. Right, I can do another break. Right, few slides about alkynes. This is still continuation of chapter 3, by the way. So why only few slides about alkynes? Because without saying that most of the reactions alkene do, alkynes will also do, because why not, right? Alkenes are double bonds, they are triple bonds, so they will just do it twice. First, triple bond be converted into double bond, and another reaction, double bond be converted into single bond. Some trivial information for you, their general formula is CnH2n minus 2. Then you put "-ine" in the end of their names, right? The element of unsaturation is a triple bond, so that's our functional group here. Yeah, as I said, most of the reactions are similar to alkenes. Very few reactions are alkyne specific, which we will be interested to see. Right, the structures of alkyne is linear, planar, because each carbon of the carbon-carbon triple bond can only make one other bond, right? Since the valency of carbon is 4, so if each carbon is making a triple bond with the other carbon, it can only make one other bond. And that's why the formula had 2n minus 2, meaning so little of number of carbons, number of hydrogens, right? So how does this happen? That, carbon-carbon single bond, and then carbon-hydrogen single bond, and then the 2p orbitals remain unhybridized. They don't take part in dehybridization. And you know what happens when they don't take part in hybridization? They can make pi bonds by sidewise overlapping, right? So with the sidewise overlapping, they will make 2 pi bonds, right? And then they need to be away from each other as much as possible. So if you only have 2 ends, 180 would be ideal, right? They are maximum away from each other. Therefore, their structure is linear and planar. So if an alkene is there, you can just paste it on the wall like a sticker. So it will not be inside the plane, outside the plane. It will be right on the plane. Right? I think the rest of the things are quite trivial. Same as all the other explanation that we did with alkane and alkene. The physical properties are quite similar as well. They are very hydrophobic because of excessive unsaturation, meaning excessive, bonds and triple bonds and double bonds. So cats are hydrophobic as well, right? The most important application of alkenes used to be in welding, not anymore. So acetylene is the common name of the most common, or not to say most common, but most simple, yeah, that would be the right way. The most simple alkyne is called ethyne, right? It's based on 2 carbons. So the common name of ethyne is called acetylene, which used to be used in welding because you can burn it at a specific point and that will generate enough heat for the metals to be joined with each other. But acetylene welding is not suitable for environment. I have personally seen this in my life, but from what I know, this is not used anymore, at least in the first world countries, right? So how you can make, or people used to make acetylene for welding, they will use calcium carbide and just add some water to it. It will form the acetylene gas, which they will burn then, and then some metal will burn, so they will be melted, and they will combine them to weld them together. That's what they used to do. Not anymore, because the reaction could go out of control all the time. Carbides are also controlled materials these days because they can be used in explosives and fireworks and so many different things. So this application is kind of obsolete. But you get the idea that acetylene gases are important in things can be controlled using high quality instrumentation and the storage facilities. I'm not too sure that if industries also use acetylene for the welding purpose. But of course, as a source of energy, natural gases are burned in industries all the time. Right? So acetylene is no different. So this is kind of the commercial synthesis of acetylene. This used to be very popular from the place where I come. Small kids will make firecrackers using the carbide, stone. Carbide used to come in stone. They would put it in a box, just spit on it as a water source, and then just leave it away, and it will blast a little bit. And you'll hear a cracking sound, which used to be very smelly because of the formation of acetylene. Now I'm thinking. At that time I didn't know, of course. I was not a chemist when I was a kid, right? Right, the other way acetylene can be formed is from the natural gas, which is methane. So methane, super important as a burner to use. So acetylene could be converted commercially. Methane as natural gas can be converted into acetylene using these industrial, temperature, time, and pressure scale, which is definitely not doable in normal labs and places, right? 1500 degrees Celsius for only 0.01 second. If you overheat it by probably some seconds, something else will form, or the whole place will blow up, because so many gases form, right? The nomenclature is pretty simple, so I will not bore you with that. All you need to do is, there's one point I need you to remember, now that we are studying it. So all other rules are still same. When the triple bond is present, instead of "-ine", you put "-ine" as the suffix of the name, right? But what happens when you have double bond and triple bond at the same position? Not to say at the same position, but let's suppose if you start numbering from one end, the double bond gets the least number, but you start from the other end, the triple bond gets the same least number. So then we have to give preference to the double bond. Do you understand what I'm saying? This is very hypothetical. Maybe it will never come in a practice question, or it may come in the practice question. I'm not too sure right now because I haven't seen the questions for alkynes yet. The alkynes tutorial is next week, right? But anyway, all the other rules are same. Only the case when double bond and triple bond are getting the same priority in terms of numbering, then you have to give preference to the double bond. Can you please remember that? Perfect. Thank you so much. Right, so how alkynes can be formed? Similarly, like we form alkenes. But we have to do the reaction 2 times. Remember that we use alkyl halides to get alkenes by dehydrohalogenation? Well, this is dehydrohalogenation for you again. That we have an alkyl halide, but here we have 2 halogen atoms. So basically you have to do everything 2 times. One time we will get alkene. Another time, another elimination reaction, and we will get carbon-carbon triple bond. Right? Now if we have halogen atom or any atoms on the neighboring groups or neighboring carbons, we like to call them vicinal groups. This is just a chemistry term. If you can't remember it, perfectly fine. Names, no need to remember. Well, if the groups are present on the same carbon, then the chemists like to call it geminal groups. Again, no need to remember. If they are on same carbon or on neighboring carbons, does not make any difference, because if you do this reaction 2 times, you will get your alkyne. As simple as that, right? Right. What are the reactions of alkynes? So alkynes can be converted into alkenes. This is a reaction that we have already seen. All you have to do is put hydrogen with the alkyne and it will be converted into alkane. If you want to stop the reaction at this point, because that reaction again is happening two times. First, alkyne is getting converted into alkene, and then alkene converts into alkane. If you want to stop at alkene, one example was Lindlar catalyst, the other example is Birch catalyst. So Birch is the German chemist, if I'm not mistaken. He was my supervisor. But anyway, these conditions give you transalkene, while Lindlar catalyst gives you cisalkene. See, this is how detailed chemistry could be. Imagine that if you are making some molecule for drug or for anything, then you need cisalkene and not transalkene, then you have to choose your conditions wisely for that. If you use trans against cis, then vice versa. So if you need transalkene, we can use Birch reduction, and if we need cisalkene, we can use Lindlar reduction or Lindlar catalyst. Right? Same reaction, no problem. Yeah, we can add anything onto alkene like we did with alkenes. So if we add water, we will get alcohol eventually. If we add hydrogen halide, we will get alkyl halide, just like that. Yeah, we can use halogen, just like we did on alkenes, to get alkyl halides eventually. You can do it one time, you can do it two times to get single bond there. Now, two reactions I want you to note down which are different from alkenes. The first reaction is hydration reaction. So when we added water molecule in alkene, we got alcohol there, dehydration reaction, right? Not dehydration, I meant to say hydration reaction. When I said dehydration, I thought that you would be clear. So hydration reaction of alkene gave you alcohol. But when we hydrate alkynes, we get carbonyl compounds. This is a totally bizarre mechanism. I don't want to go into the detail of it. But then, this reaction is done in the presence of mercury sulfate. Sulfuric acid was there as well, so the difference between alkene and alkyne is the presence of mercury sulfate. No need to go into further detail. The difference is that when you hydrate alkynes, you don't get alcohols, instead you get carbonyls. While alkenes, when you hydrate them, you simply get alcohol. So one of the difference between the reactivity of alkenes and alkynes. The other difference, which is super important, and the last slide of this chapter, that when we have alkyne at the terminal part of the carbon chain, right? So carbon-carbon triple bond could be somewhere in the middle of a chain or at the corner of a chain, right? So when it's in the middle of the chain, no problem, everything is normal. But when it is present at the corner of a chain like that, which means that it will have one hydrogen because it's at the corner now, right? So this hydrogen is a little bit acidic. And this can do acid-base reaction if you use the right strong small base such as sodium hydroxide or sodium amide. So sodium amide, this base is called sodium amide, which is even stronger than hydroxides. So what happens is that this base can abstract this proton and the electrons will move towards this carbon and we will get this strange looking carbon-carbon triple bond bearing a negative charge anion, which is called acetylide, as the name suggests. The formation of acetylide. So this acetylide anion is a work of wonders. Wherever you want to put a carbon-carbon triple bond, if you are making something where you need a carbon-carbon triple bond, this is how you can introduce it. First, you get a terminal alkyne, just like that. You react it with sodium amide, you will get the acetylenine, and this acetylenine can be put anywhere you want it to be. If you react it with alkyl halide, the halogen atom will be removed, an acetylide atom will attack on this carbon, and you see the formation of new carbon-carbon single bond. But in doing so, what we have actually done, we have done two things. First is that we have made a carbon-carbon single bond, which is very impressive, isn't it? Before this, all the reaction that we performed, we never made the new carbon-carbon single bond. But why using acetylide is important? Because in doing so, we have also introduced a carbon-carbon triple bond in the molecule. So this is a very cool reaction, very easy to do reaction, and the most obvious way of introducing carbon-carbon triple bonds in a new molecule. So your base molecule was this here. This was your starting material, right? If you want to introduce a carbon-carbon triple bond here, this is how you could do it. So this reaction is characteristic of not all alkynes, but only of terminal alkynes. So this is the second reaction, which is different in terms of chemical properties of alkenes and alkynes. Does this make sense? Any question? Right, so I owe you 5 minutes break. You can take it now. In the meantime, if you have any questions, you can ask me. Or probably we can do 3 minutes. Alright, I said 5. Well, I have been recording the lecture, but I forgot to on the mic. Alright then, never mind. There's nobody there anyway.
There's only one in the room.
He said no.
Alright, fine stop, fellas. Let's begin the chapter 4, which is aromatic compounds. Alright, this is what we will be doing in this chapter. The main focus for today's discussion will be about what aromaticity is. Right, we will probably see some of the nomenclature of the benzene derivatives, while the reaction and orientation, I think we will continue in our next lecture. So for a molecule to be aromatic, it needs to follow 1, 2, 3, 4 of these criteria, all 4 of them. This is also super important for your exam as well as for your understanding of organic chemistry, which will help you in the understanding of biochemistry as well. So for a compound to be aromatic, it must be in cyclic form. The structure must be cyclic. Second thing is that the structure should not only be cyclic but also be planar. Right? Remember, just now we were talking about planar structure of alkynes and how alkenes are also somewhat planar, trigonal. So, for a compound to be aromatic, the structure should also be planar. Point number 3, which compound needs to follow to be part of this awesome aromatic group, is that they must have each atom of the ring a p orbital that's perpendicular to the plane of the ring. This is the exact thing which chemistry requires, but for you to keep remembering is that you should have a conjugated or alternative single and double bond. Right? So all these 3 things actually mean the same thing. In a molecule, if we have alternative single and double bond, that's what this whole statement means. Or if the molecule has a conjugated double bond system, the whole thing also means the same. Or what it actually tells is that how you can have this quality if all the atoms have the orbital that's perpendicular to the plane of the ring. That's when you will have the conjugation or alternative double bond formation. So if you don't understand this whole lining, that's totally fine. You can just remember that you should have conjugated system of pi electrons in the ring. Or, more simpler, that the molecule should have alternative single and double bonds. Alright? That's criteria number 3. Criteria number 4 is that the molecule should follow Huckel rule. So what is Huckel rule? That the number of its pi electrons should be equal to this number, or this equation I should say. That the number of pi electrons should be equal to 4n plus 2, where n could be any number, including 0, 1, 2, 3, whatever. So if the number of pi electrons, I'm not saying pi bonds here, keep this in check, that we are talking about pi electrons in this case. Here I was talking about bonds. like alternative single and double bond. Right? But in this case, we are talking about pi electrons. So the number of pi electrons in the molecule should be what? 4n plus 2. We'll look at these examples and you will understand everything. These are aromatic compounds. What? They are cyclic, they are conjugated, they follow 4n plus 2 pi electrons, and their structure is flat. The perfect example is benzene. Why this is important? Because they are unusually stable. So when some reactions are going on and the fate of the reagent can make the product as this molecule, then the whole nature would want it to work in that direction and make this sort of molecule because of its unusually stable characteristics. Right? Now, cyclic you understand, right? Because it is a closed chain structure. Conjugated, as I said, alternative single and double bonds. Double bond, single bond, double bond, single bond, double bond, single bond. Alternate, right? 4n plus 2 pi electrons. So how many electrons benzene ring has? 2, 4, 6. Right? Now if you put in this equation n equals 1, then what you will get? 6, right? So 6 is a Huckel number. That's what we call it. So the ring should follow the Huckel number, which is 4n plus 2. So benzene follows Huckel number, therefore it follows the Huckel rule. Finally, the structure must be flat, so yeah, benzene is pretty flat. Therefore, this is aromatic compound. The reverse of it is anti-aromatic compound. These are unusually unstable. They will still be cyclic, they will still be conjugated, but instead of Huckel number, they will follow this number, which is 4n pi electrons. So here we have 4n plus 2 as Huckel number. This is just 4n number. For example, this molecule fits the bill completely about aromatic compound except for Huckel number. So this is an example of anti-aromatic compound. Very unstable, very difficult to form, and just there for some small time. Right? As it says, only stable below minus 100 degrees C. So if someone needs it, then they will be working at minus 100 degrees. Another possibility is that some compounds which are simply called non-aromatics. This is not a different class, but if a compound follows all of these rules, but any one rule is not following, then you can simply call it non-aromatic compound. So this is not a separate class. If you don't remember it later, that's fine as well. As long as you can understand and remember aromatic and anti-aromatic compounds, you are good to go. But just an example is, this molecule follows everything, but the structure has some flexibility. So it's not flat anymore. So because of that reason, it's neither there nor there, so non-aromatic. So now clear, right? The 4 criteria. What is Huckel rule? Why it needs to be this? Now why there's no answer to this? That why is it called like aromatic compounds? Probably from the fact that most of these compounds have weird smells. Aroma generally means fragrance or something, right? But I'm not too sure. That's just their names. And anti-aromatic, that's just their names. Probably, if those were fragrant compounds, then what about anti-aromatic? They take away the fragrance of things? I don't know. That's just their name. That's the reason that I say that there's no information about why they are called this and that. Speculation that aroma is fragrance or something that smells, so that's why aromatic. But it's important to note that aromatic compounds are super stable. And nature makes a lot of aromatic compounds. Those are also very, very important. Against them is anti-aromatic compounds which are not stable at all. Right? Now the most important aromatic compound is of course benzene. Some trivia. I will not bore you with this. Right? I think everyone knows how benzene was formed and how the structure was developed. Right? So some people, I mean it's all fiction I think. The people say that Kekule saw the structure in his dream. Yeah, it's not like authentic information, but you can find it on the internet or something. That he saw a snake eating its tail, so that's what gave it the idea that the ring of electron could be circulating in the cyclic structure. I mean, this explanation is fine, but then how do you come up with these rings and all? So this is all totally folklore for you to probably just note down. But the important thing is that this structure was later experimentally proven. So we are people of science. We will talk about experiments and data and these things and not about dreams. So what happened is that when they did the reaction of benzene with bromine molecule, so they found that the two bromine atoms, one time they were between the carbon-carbon double bond bearing carbons, and one time they were in carbon-carbon single bond, so hence both of them are equivalent. That's what strengthens the dream of Kekule, and this structure is called Kekule structure of benzene. So you can make the double bonds here or there, it does not make any difference, right? Or if you want, you can simply make a ring inside. That's also perfectly well. The only thing to note down here is that right, so you remember the resonance forms, right? We studied in chapter 1. So yeah, these different structures would be the resonance forms of each other. While the actual structure, which we call there the hybrid structure or something, right, would be something like this. So when we say something like this, it means it's somewhere between single bond and double bond, right? So that's why the bond order is 1.5, right? And the bond length is also between what it should be for single bond and for double bond. So these things are experimentally proven. So we are not talking about folklore or any sort of superstitions or dreams. This is all experimentally proven, right? So just to compare, we have the double bond, normal double bond, which is like conjugated in this case. So the length would be 1.34 angstrom. While for a conjugated system, single bond, the bond length would be 1.48 angstrom. While for benzene, it's just there in the middle, 1.397 angstrom. So it fits the overall explanation of Kekule, right? That the bonds are somewhat between single bond and double bond, right? Right, so the structure, now you can refer back to the long statement, which I simplified when I was telling you the criteria for the alternate carbon-carbon double bond and single bond. So the actual thing is, in like molecular orbital theory, that each of the carbons should have a p orbital which is perpendicular to the plane of the ring. So if the ring is there, then the orbitals would be kind of there, right, behind and above the plane. So these are the required orbitals on each of the carbons. These orbitals can make, this can make a pi bond with this as well, and this can make a pi bond with that as well. So that's what it means by a conjugated system. So generally we'll have an electronic cloud as a sandwich, and inside, you can just consider this as a cheese slice. You can consider them as burger. Probably I'm hungry. So yeah, that's what it looks like if you compare it with anything else. Right? There are several other important aromatic compounds there as well, such as polynuclear aromatic hydrocarbons. So we have naphthalene, anthracene, phenanthroline, phenanthrene, so on and so forth. These are also somewhat important. So this is their structure. Funny looking, right? It just looks that the nature has combined many benzenes together. So some of them are natural, but most of them are artificially made or are side product of some of the utilization of other things. So polynuclear aromatic hydrocarbons, PAH. This is an important acronym if you are studying environmental chemistry. These molecules, remember, are super stable. So if they are somewhat exposed into environment, then they will be there for the rest of eternity. And they could cause all sort of trouble to the environment, to the wildlife, to everything. That's why they are an emerging class of environmental pollutant, PAH, polynuclear aromatic hydrocarbons, yeah? And they are generally side products of some of the reactions going on in industry or even nature. I'm not too sure about nature, but 100% industrial side products. Yeah. So like benzene, if you have any aromatic compound, you can make the resonance form structures by moving up the electrons, right? So these electrons will go here, will go here, and will go here. Or you can just keep moving them, and you will have the other resonance forms, right? So yeah, in here we have two benzene rings fused with each other. So the simplest PAH would be naphthalene. So naphthalene is still, I think, used to keep the bugs away, right? Have you seen at your household the small, pills of naphthalene? For some reason, they have a funny smell which bugs don't like. So that's why they are still used in household applications like that. Well, we can have larger polynuclear PAH as well. Yeah, so you see that they are formed in combustion of different things. Smoking as well, I guess. Many of them are carcinogenic, so they are cancer-causing agents. As I was telling you, that super harmful for the environment as well as for living organisms. Some of the examples are here, such as dibenzopyrene, benzopyrene, or pyrene, right? Again, trivia for you to read. I think it says what I have been saying for a while, that these are all unimportant stuff, unwanted stuff. What we need to do is detect them from the environment and try to establish methods by which we can eliminate their entry in the environment. That's first thing. And if they are there, how we can dissolve them, or how we can dissociate them into things which are not as harmful to the environment as these are, right? So this is an important area of research in environmental chemistry. Right, so their structure, when you were looking at it, like so many benzene rings and hexagonal rings, so I thought that you would be thinking about allotropes of carbon. That's why this slide is there. It has nothing to do with aromatic compounds. But you know, right, that carbon is formed and found in different allotropic forms. The major ones are these: diamond, graphite, and graphene. So if you look at this structure, this is what we were talking about when we were looking at the PAH, right? So just for comparison. Yeah, you know this already, right? Graphene, graphite, diamond, all of them have carbon arranged in different forms. That's what gives them different properties. Yeah. So as I said, this has nothing to do with pH, but since we were looking at those structures, so I thought of these. So then I thought that probably you will also think of this. That's why I did this slide, if it makes any sense. Right? Right, let me see. Yeah, probably 2 more slides. So fused heterocyclic compounds, like first we had the other examples of fused aromatic compounds where we didn't have any hetero items. So when we say homo items, it simply means carbon. When we say hetero items, it generally means any atom which is other than carbon. So we can have fused systems of rings where not necessarily all items are carbon. So these are a few examples of that. That's the only reason for me showing you these molecules. However, it's also important to note that these molecules are also super important because some of them are drugs. For example, quinine, very good against malaria. LSD, very good for very bad things, right? And then benzoderone, which is a vasodilator, so another drug. Tryptophan, amino acid related molecule. So these are just a few examples of fused aromatic systems with a hetero atom, right? For their physical properties, remember the first point I also covered in our practical 1, that since they have higher percentage of carbon as opposed to non-aromatic compounds and normal compounds, so when you burn them, the formation of soot happens. When we say soot, it means black smoke is formed. Why that occurs? Because carbon is essentially coming from coal, right? So coal is black. When it's burned, you get blacker soot. That's how you can identify aromatic compounds from normal compounds. Yeah? Their structure is super symmetrical as we have been seeing, and then they are super stable as well, which means that they will be difficult to melt, and their melting point will be higher, their structure will be stronger, your boiling point will also be higher, right? Ortho meta para, don't worry about it, we will cover it hopefully in next chapter. Well, that's about it. Thank you so much, everyone. I will see you in next class. We still have 4 minutes, which are reserved for questions. Do we have any questions so far? I need to make a note there and stop there.